Okay, so good morning to everyone. Welcome to this session. First of all, let me introduce myself. My name is Plut Galatsopoulos. I'm a Principal Product Manager in Arm's Research Enablement team. And in today's session, we're going to talk to you about accessing Arm IP for education and research. So we have quite a packed agenda, and we were a little bit delayed. So hopefully we can cover everything, and you will find all of the sessions interesting and engaging. We will start from Frank Boisier from European Commission. He's going to talk to us about opportunities and challenges in the IoT era. Then I'm going to come back on stage and I'm going to talk to you about research enablement and DesignStart offerings that we have for you. Then we have Jialin Du from Arm Education team. He will let you know about Arm technology in education. Then we have Professor Ed Davis from North Carolina State University, who is going to share his experience using Arm IP, and the title is Experiences Using Arm Technology in Education. A coffee break, if we can make it, hopefully we will. And then we have 3 more sessions. At the second part, Professor Luciano Ost from University of Loughborough will talk to us about the multi-ARM processors platform. Then we have Professor Koldo Bastexera from University of Basque Country. He will talk to us about experimenting with neural processing SoCs. And last but not least, Professor Tang Chong Ming from UTIAR University of Malaysia, talking to us about Raman University multiprocessor system. So without further delay, Frank, please come on stage.
Good. Good morning, everybody. I wasn't sure exactly who I will be speaking to today because when I look at the program, I saw a number of interesting topics and many people with different backgrounds, computing, more microelectronics, more application areas, more domains. So I've made a fairly long presentation, which I will sort of select some slides from and leave the whole presentation for you for further reference. So what's really IoT, I think, is part of the question. And the answer doesn't really matter because we will see that IoT is really everywhere in its number of applications. It's a lever for change mostly. The Internet of Things is actually being used as a transformation vehicle in all sorts of domains. And there I've taken some slides here and there from the various industry partnerships we're working with. And I think what I want you to really take out of that is it's really everywhere, and anywhere you can have an application in that domain. And what matters is not really where it is, but the fact that it's being everywhere. And that has been driving a lot of our thinking on what do we do in support of research and policy and legislation in the European Commission. And I started also preparing a slide on how Internet of Things is being addressed in our various departments, but I gave up because it's even more complicated than what we saw this morning about the organization of Arm. I mean, you have all sorts of departments doing a bit here and there. But really, first, we have a lot of research activities involving universities and industry in the micro and nanoelectronics domain, and we are covering all sorts of domains, and there are all sorts of priorities for activities. There are some groups in nanoelectronics, in integration of this in microsystems, also in new technologies for the electronics, including the bio and plastic kind of developments. I think what's important there is all this development. Internet of Things is one of the main applications of this development. It's not the only one. You have also high-power computing and all these kind of things. But what matters today is really there we're talking about the thing of Internet of Things. This is where the microelectronics gets into. And all sorts of then more macro objects which are becoming autonomous and are being integrated in an overall system. One of the important things is Internet of Things is being mentioned as one of the main drivers of growth for microelectronics. That's also the one of the main killer applications for 5G. It's also the main driver of digitization of industry, and it's really everywhere. And I think one of the unique features we have in Internet of Things is it is the combination of what you have on the left, this column with micro nano electronic software and 5G, which is basically wireless communication, which are basic technology development areas. In the middle, there are some sort of what I would call macro disciplines, which are new developments, which are taking advantage of combination of technology, but this is really new way of doing science. And Internet of Things is really one of the very few areas where all these things actually come together, but with a purpose. The purpose being the digitization and the new kind of intelligent products that are coming into the market. So that is autonomous driving, that is smart factory, that is smart living and augmented domestic activity with smart appliances, healthy aging, digitization of industry, you name it, whatever you want. But I think this is what the purpose is. And then you can really look at the various value chain. I think what this shows is what's important is to know how the value is actually building up, where it's being added up. And one of the things where we have put a lot of emphasis is on the multiplicity of this value chain and the fact that beyond working on basic components that are software, communication, and microelectronics, when we're going to the higher level of the application, we are mostly interested in the common elements across these vertical value chains. What are the common building blocks and having interoperability between them? And I think that our approach to the world digitization of industry and digital innovation is about product, process, and business models. And really, one of the driver there that we see, and it's extremely true in the Internet of Things, is to have these cross-cutting business models. Basically, what we see is that successful companies, they do start in one value chain because this is where they do their first prototype, where they have their first knowledge in the beginning. But very quickly, if these companies are working and successful in developing their product, then they move aside. And after entering one market, it can be smart farming, then they can get into other domains like smart cities and so on and so forth. And this is by multiplying their actually technological offers that they can get into markets. And if they have this approach, which is about having multiple business models in different domains and have a cross-cutting technological approach, then they can have a lot of success. And I was very surprised in the Internet of Things week that took place in Bilbao in June this year, that one of the CEO of the company that was making one of the keynote speech, this is exactly what she was saying, is that the success of a company that was about that is they entered the market with some products about smart cities, measuring certain things. And very quickly they diversified, and they have entered many other domains, farming, fisheries, smart cities, and they are starting also in environmental monitoring, in energy monitoring, and so on and so forth. And that is because they have been using this approach, and they have been taking advantage of what we have been doing and supporting in our research program. There are no more elements. I will not go very much in detail, but there, I mean, the importance of digitization of industry and the digital transformation of all the domains, I think we are measuring that very quickly, and what we see is that per country is very much underexploited today. There are huge opportunities for improvement in this domain, getting better value, better products, better services, and so on and so forth. It's something that we are monitoring. I've been saying, and we are monitoring the digitization of Europe and European society index every year in May, where we are measuring different components of the digitization of the society per country, per sector, and invite you, if this is something of interest, to have a look at that. Now, in order to support that, we came in 2016, in April 2016, with the digitization of European industry. It was partly a policy program, but also very much a research activity and support for that. And it has different elements. It has an element of course, digital innovation, leadership in research and innovation. So basically there we are talking about the research programs. And this is what I will concentrate a bit more, the last part of my talk. But there's also things about regulatory framework and training and education. Really getting people skilled to do that is an important subject, which I will not really get into today. So as part of this digitization of European industry, Internet of Things is one of the major drivers. And there we have specific challenges. One of it being in interoperability, but I think one of the most difficult one to crack is this chicken and egg problem, where you have the supply and the demand side, who are both expecting something from the other side. So the demand side would like to have better solution from the supply, basically from all levels, from the microelectronic, the communication, the subsystem, everything. They would like to have better products for them, but those products, they don't really see them coming in a way that is fit for them to change their business processes. And that is simply because the supply side would also like to have a better requirement expression from the demand side, in order so they could meet and see what are the solutions that can be developed and at which level these solutions needs to be developed. Then there are other aspects which are important, in particular dealing with the non-technical aspects, all the regulatory environments, the policy environment, the security aspects which needs to be taken into account in developing solutions. And in the end, the question of acceptance of new products and technologies. And I think that's also very difficult. And this is sort of bringing the chicken and egg problem to another level, because even if the solutions may be there, so you think, if they are not accepted, they are not worth anything. I mean, you really need to get them used and make what's necessary to have them used, which may be things which are not related to technology, but are related to organization of the work, understanding more how you can use it, sharing the business benefits also across value chains and across actors in a way that's different. So there are lots of challenges there. Now, what do we have in our reply, and what do we see working in our reply? We have a number of what we call the large-scale pilots. At the moment, we have 5 of them running in domains like autonomous driving, smart farming, smart cities, e-health, and assisted living, and wearables, and large city events. So these are domains. We are calling for more of those. They are called for proposals that are open at the moment in other domains. And these are projects which are fairly large. We're talking about between 15 to 30 million euro funding per project. Projects of about 3 years. And projects which also have They are not just big monolithic projects, but we want them to drive the change, and we ask them to have what we call open calls, and I'll come back to that quickly, which allows smaller participants and new actors to join into these large projects and take benefits of the progress. We have also project clusters where we actually cluster project by topic in order to also capitalize on their results and go beyond what a project can achieve to have more impact. And there I'm thinking about a cluster on IoT security that has been launched this year, where we have 8 projects which are running, and they are not only going to do what their project do, but also pull together common results to have more impactful results on the domain. I think also one of the strong elements of interest in what we do are the public and private partnerships we have. There we have them we have the Alliance for IoT Innovation, AOTI. There's the Big Data Value Association, the European Cybersecurity Organization, the 5G PPP on communication, the Excel joint undertaking on microelectronics. These are important because it is a way to pull together funding from the public sector and the private sector and make sure that we have large projects and large impact. And these partnerships are important, and they will be even more important in the future. I'll come to that at the very last part of my presentation. So this project we've been running, I mean, we have been gradually augmenting our funding and also augmenting the scope, yet keeping a common focus, and in particular this focus on platforms and interoperability across various sectoral domains. These open calls we have been using there, basically they are competitive calls where some of these projects are seeking for new use cases, new technologies to be integrated in their common architecture and common framework. And these are very big opportunities for very small setups, even sometimes just one single company can apply. You don't have to build a consortium. You can apply and you can have a lot of results. So if I take the example of the one of the cluster that actually is now coming to an end, we have organized 10 open calls. We have had hundreds of new participants joining this cluster of projects with small projects. You can do the computation, so it's not a lot of funding, but it's easier to get into these activities, and it's a shorter-term activity support, so it's more focused, can be much more impactful. And if I just take a recap of some of the calls we have been doing and we are planning just in digitizing of European industry for smart manufacturing or smart anything everywhere initiative, there are calls which have been launched regularly by some projects on specific topic, and this is something that's continuing. There's a continuous opportunity for that. They're all published centrally in one page. You can find all of them. They are published regularly. At the moment, for Internet of Things, there are 3 big open calls, which are in smart farming, active aging, and smart farming, active aging, and autonomous driving. They all have open calls which are open at the moment and will close in a couple of weeks. And for all these things, basically, well, there's a bit of work to do. You don't get in a large project like that just to do what you want to do. You have to do your homework to see how you can benefit and plug in your solutions into what they do, understand what the platforms are. So you may fit or not fit in some of that, but that's for sure an opportunity, and there's a lot of webinars which are organized to help potential proposers to prepare their bid for that. Another element that we're promoting is what we call the digital innovation hubs. basically these are instruments that where we want organization to work on the local level, on the regional level, being able to bring the supply and the demand side together and to try to find solutions. There we are sort of supporting them. In particular, we're supporting them also networking among them in order to promote best practices from one to the others, and also sometimes go and seek the supply if it's not available locally, or when there's a supply which is interesting, also to find better users also in other domains. So it's really one very important tool, and I think it will be an important tool that we will be using also in the future, because you may know that our research program will launch its last call for proposal next year, and we'll have a little bit also in 2020, but after that, this is over. And there we want to continue developing a number of things which I've been mentioning before. These digital innovation hubs, these public and private partnerships, the kind of partnerships we have, and these are something we want to support. So the rest of the slides, I will skim through them. I will leave them for you for reference, because I think this is preparing the future. So the Commission has made a huge proposal for what will be its budget from 2021 to 2027. And as part of this proposal, all the digital support is very important. And we want to Europe to be really in the driving seat there. We will have a number of things. We'll have the Horizon 2020 research program will be evolved into what's called now Horizon Europe, where we will continue to address big challenges: digital and industry, digital and health, mobility, environment, continue all the open innovation and open science research infrastructure. In addition to that, there are a number of other programs which are going to be used. You may know about the Connected Europe facilities, but I mean, this is basically going to continue in order to support pan-European infrastructure. Basically supporting the rollout of 5G across Europe, but also supporting infrastructures for transport and energy. But on top of that, we're going also to add something which is new, which is a Digital Europe program, where we are going to fund capacities which are essential and unique for Europe. And these are, for example, high-performance computing, artificial intelligence resource centers, working on cybersecurity centers, and so on and so forth. So we will have the three elements. These are very initial proposals, and I will show you a bit later where these things are. So I skipped through that because we can spend hours talking about that. I leave that for your reference. All I want to mention is that the IoT sort of higher level vision I've presented will be embedded under the next generation internet cluster of activities in this program. But all of these are still in the preparation, and this is also why I'm presenting that to you, because I think it will be important that you move in and you express your support for what you really want to be done in this program. So I'm skipping all that because I don't think that's the most important thing. One thing I want to highlight is where we are today. Basically, we've made this proposal in May. We have had the first discussion on that, but you see that in 2018 and 2019, we'll have European Council meetings, so this is meetings of head of states that will agree on that. And in order to prepare these programs and develop better what are their objectives, what will be their priorities, and also their level of funding, we need more input. We need more input. We're preparing our contributions, but I think this is where we can have input. And As an example, there was a report that was presented in June this year to the Commissioner Gabriel. There was a report presented by the main European CEOs of microelectronics industries and universities. And some of the recommendations they made, I think they came in support and resonate with what I've mentioning, what we want to do with digitization of European industries, to extend these partnership programs we have had until now, and to sort of rethink and look at bigger challenges, because really what we see is that they all have some priorities, some interest, but where the most important work and the most important innovation can be done is always at the boundary of 2 or 3 of them. So we have to sort of find a way to organize better, to really better address these kind of things. The smooth innovation from IP to product, I think this is exactly what this session is all about. And I think that's one of the very important things we want to do. We have started to do that by ensuring that the support to the microelectronics research project were also driven by use cases and applications. So we are a bit into that, but I think we need to go further into that. The initial innovation hubs could also be very instrumental in that domains, and so on and so forth. I mean, really, again, we have the skills there, and I think this is one of the kind of reports contribution can be useful for building up all the new program. Of course, you have this point of view, but we have also other point of view from other sectors. And the point will be to say, well, how can we add up the demand to have a common program that makes sense, rather than having one fighting for the other and trying to get a better share of the cake. So really there, we want to see how we want to go. So all in all, this is what we're doing. There are many examples I could have used, but I think it's better if we can have discussion also later on during this session or during the break, because many of the projects we have wonderful results in all parts of Europe, but also in other parts of the world, in Africa, in Brazil, in Asia. We have a lot of cooperation, all of which are always based on very important developments which have been done in Europe. And I think we have to be proud of what you are achieving in this research project. So with that, I think that concludes my very quick overview. I realize that's a broad flight over all we can do, but really we're not talking about large programs. Thank you. If you have questions, whatever.
What's the allocation for, or rather, how much is the allocation for the skills development section? The last slide.
The one.
No, the last one. The very last.
Right.
No, the next one, sorry.
No.
Create a task force for electronics education.
This is a report that's made by European CEOs to the European Commissioner for Digital. And so that's a proposal. That's not a proposal that comes with a budget. And I think when it comes to the budget, I think there are 700 million which are just developed to advance digital skills in this Digital Europe program. So it's for developing basic infrastructures for that. But also, I mean, that's also to be seen in the conjunction of the whole program. And I think if you go back, I mean, no, I don't have it at this level. But I mean, really, this level of breakdown of funding will be clearer in the next proposal. And I think this is also part of the question. Taking into account also that the funding there, it's a tricky thing, because if you talk about education, that's national prerogative. So that's not something where Europe can intervene a lot in financial support. But there are things we can do to improve that, to improve the impact. So there we have a lot of multiplier effect. When you talk about skills, there's also the skilling of people which are already working, and that's basically, we're talking there about private funding. So really, this is why these strategic public and private partnerships are important, because that's a way to make sure that this sort of almost $1 billion funding from the European Commission is not just alone doing something, but that just one contribution around which we can multiply and add up activities and have a better impact. So really, I mean, digital skills is a huge program. If you're interested in that, I can put you in contact with my colleagues who can be more specific and more effective in answering your questions. Other questions? No? Well, anyhow, I'm there. You have my coordinates if you need help. Thank you.
Okay, so let's look a little bit into the ARM offerings for the research world. And I'm going to talk to you about research enablement, what research enablement is, and the DesignStart program and what it has to offer for you. But taking a step back, the path to successful research, we all know it can be rough. So doing novel research, thinking out of the box, and creating new technologies were never meant to be trivial tasks. That's why we have some of the greatest minds like yourselves working on all these things. However, in many cases, research can be tough for all the wrong reasons. So not having access to the right infrastructure is not very helpful. And this is one of the things that we would like to focus on and make sure that we're enabling you with the right technology and IP from ARM to make your path a little bit smoother. So what we have to offer is ARM's world-class technology, along with our expertise and guidance. And we hope that this will make your path towards successful research a little bit more stable and easier to go through. So ARM has a long history of creating strong partnerships in the commercial world. We are licensing our IP to our customers, and we are always getting surprised by the new innovative products that are coming to market based on these. So we would like to replicate a very similar model with the research community. We want to enable you with our IP and get surprised and amazed by the great research results that you will achieve based on our technology. And we believe that doing research based on ARM, it's going to be easy and smooth, so you don't necessarily need to use RISC-V unless you want to hack your own instruction set. Hopefully, after the end of this session, you will see that we are taking research enablement quite seriously, and we will keep bringing new products, research enablement products to you. So here is an overview of what we have to offer now. ARM is a hardware IP company, so if you want to put together a novel SoC, we have all the building blocks for you to do that. We have processors, interconnects, peripherals, so that you can put your system together, you can simulate it, you can prototype this on FPGA, and then if you want to take the next step and produce silicon based on that, we also have lots of physical libraries for you to take and do the implementation. But no matter how far you want to take your prototyping, you will always need software and tools to run on top of your system, and we have lots of them to offer as well. So if you want to do software debugging and you want to do performance profiling of your applications, we have DS5. We have EmbedOS, which is an operating system specifically designed for IoT devices. And we also have machine learning libraries to optimize the performance of your machine learning applications. So we have compute library that runs on top of Arm Cortex-A CPUs and Mali GPUs. And we also have CMC Sandlin, which runs on top of Cortex-M CPUs. But in many cases, your research is going to be focused on one specific area, not in putting together a whole SoC. So having a good reference starting point is going to be really helpful. And that is what DesignStart can offer you. It can offer you complete subsystems based on Cortex-M0 and M3 processors that you can use for software and hardware co-development. And also, we're happy to announce today a new product in the DesignStart family that I'm going to talk to you about more later today. And you will see how we are expanding the technologies and the offerings for you in order to do more novel research in high-profile research areas. So if you don't want to do your prototyping on RTL, we also have lots of software simulators to offer. So we have Gem5 for architecture exploration on both CPU and system level. So even if you want to do your own instruction set and experiment based on a software simulator, Gem5 gives you the capability to do that. But if you want something simpler, something to use out of the box, and just do software prototyping based on that, then we have the fixed virtual platforms. So let's look a little bit more into the building blocks. So ARM has lots of different IP to offer you, and we have different delivery mechanisms that go along with them, depending on the complexity of the IP. So we have the DesignStart program, which can give you very easy access. You can just go on our website and have a click-through license, get your IP within a few minutes. But then when it comes to more complex IP, we have a little bit more stringent process. So it will have to go through some approvals, and then we will have to sign off some legal agreements. But we are taking steps to simplify this process as well. So as you can see, we now have a list of pre-approved ARM IP that you can have access to and make this release process a little bit smoother and a little bit quicker for you. In this list, we have added Cortex-A53, Cortex-A5, and Cortex-R5, along with all the interconnect components and all the peripherals. But even if you want to do research based on more advanced technology, please don't hesitate to come and talk to us, because if our research goals are aligned, then we can offer you even higher-end IP. And here are a few examples to support what I have just said. So we have participated in a big number of high-profile research projects, starting with the Human Brain Project, which is investigating neuromorphic chips. We have enabled them with Cortex-M4, and you can find 144 instances in the prototype chip. We have EuroExa, which is an EU-funded project for HPC, and at its heart sits Cortex-A73, one of the highest-end processors that we have available, and we have provided this for this project. We also have Cortex-A53, which we have provided to NASA so that they can harden it and take it to space application, which is really interesting. Also Mont Blanc, another HPC project based on Cavium Thunder X2 with Arm V8 architecture. Uniserver, a microserver ecosystem development project that is based on Applied Micro's Arm V8 architecture. And last but not least, we have provided Cortex-A53 to IMEC so that they can do co-optimization of the new process nodes with cutting-edge IP like the A53. We also have lots of physical IP to provide you, a very wide range of process nodes from 250 nanometers all the way down to 14 FinFET. So we have standard cells, memory compilers, even specific optimized libraries for performance, area, or power, and even some hard macros for particular processors that we are providing. We are also having a very wide range of foundries that we can support with our libraries and process nodes, and you can see them over here. And another thing that I would like to mention to you is that we are in discussion with Europractice to help you accelerate taping out silicon even further. So in case you don't know Europractice, which I assume you do, because they are very well engaged with all the universities and with research organizations within Europe, they are the go-to person for EDA tools and for helping universities tape out silicon. So apart from the ARM IP that have been developed by our commercial groups, we also have some IP that they have been designed by Arm Research team, specifically for the needs of the researchers. So we have one example, ACAI, which stands for Arm Coherent Accelerator Interconnect, and it is providing you with all the infrastructure that you need so that you can easily plug in your hardware accelerator on an ARM-based system. So ACAI has configurable L1 and L2 caches, so you don't have to design them in your core hardware accelerator. And it also has an MMU for virtual to physical address translation. Last but not least, it is connected to the ARM CPU through an ACE interface, so it gives you full coherency, and you can maximize your performance in case you want your application to run on the same set of data on both CPU and your accelerator. So moving on to system modeling with software. So we have Gem5, which is an open source tool that we are using very extensively within ARM for our own prototyping purposes. And we are also providing lots of these components to the open source community so that you can do your own research based on these. We have lots of components that we are offering. We have in-order CPU pipelines with or without a timing model. We have out-of-order CPU pipeline without timing for the time being. We have also provided you with SVE, the Scalable Vector Extension of ARM v8 architecture, so that you can very accurately model all the SIMD capabilities of our latest generation CPUs. And we actually have a workshop dedicated to that later that you can attend if you're interested in software modeling. We're also providing you with lots of SoC infrastructure models. So crossbar-based SoC interconnect, memory controller with quality of service, and even a display processor, which is quite important because this allows you to run rich operating systems like Linux and Android on top of Gem5, similarly to what you would have been doing on a physical hardware platform. Therefore, you can have really realistic workloads for your model. So even though Gem5 is a really strong and powerful tool for architecture exploration, the feedback that we got was that the learning curve for that can be a little bit steep sometimes, and we wanted to help you get started easier. So we have created some reference systems. We have the high-performance in-order CPU reference platform that you can use off the shelf, and it is ready to run software on top of that. It has an in-order CPU along with all the right interconnects, infrastructure, and software. And we are planning to do more of these reference platforms for additional systems in order to make your research based on Gem5 a little bit easier. Also in the future, we are planning to bring lots of other components to the open source community. So we have SMMU, we have a mesh-based interconnect that we are providing to support advanced topologies. We have DP650, our more advanced display processor. And last but not least, we're going to bring a fully featured ARM v8.x architecture to Gem5 and a state-of-the-art out-of-order CPU on that. So moving on to fixed virtual platforms. As the name implies, they are fixed, they cannot be modified, so not a good fit for architecture exploration. That's what Gem5 is for. But they are very easy to use, very easy to access, and you can run your full software stack on top of them. They give you the full programmer's view, and you can actually have ARM v8 architecture FVP freely available through the ARM developer website. If you want to model the specific feature set of a particular ARM processor, we also have FVPs for pretty much every single CPU that we have developed. So you can come and talk to us, and we can enable you with the right model. So let's look into DesignStart now. So as mentioned before, DesignStart was meant to provide you with fully blown systems so that you can have a great starting point. And these systems are currently based on Cortex M0 and M3. These are one of the most proven processors in the world. There are actually 28 billion different devices out there using Cortex M0 and M3. So you can be sure that you're doing your research based on good foundations, and that there is a really strong ecosystem of software and tools built around these processors to help you. So the way we are providing our DesignStart offerings, they come in 3 different flavors if you want, depending on the objectives that you have. So we have the first and simplest, which is DesignStart Eval, if your purpose is to evaluate a system and do some teaching on that. So you can have instant access to that through our website with click-through license. You don't need any further approvals, and you can get our deliverables within just a few minutes. We have DesignStart Pro Academic, which is for a little bit more advanced use cases. So if you want to do a silicon based on M0 or M3 DesignStart, then this is the right deliverable for you, because it is providing you with full RTL of the whole subsystem, while the eval is having obfuscated RTL of the M0 and M3. And this is, again, a simple click-through license. We're just expecting you to let us know about the use case and how do you plan to use our system. And you can actually produce silicon. You can have 1,000 units completely free of charge. Then if you want to commercialize your research and take it to market, then we have DesignStart Pro, which has, again, a simplified contract, but it needs to be paper signed, and then you will be paying some royalties from shipping more than 1,000 units. And we're very happy to see that we had really good success for all of these 3 DesignStart delivery mechanisms. So as you can see, we had more than 3,000 downloads in the last 12 months for DesignStart Eval. We have more than 200 different research organizations having access to DesignStart Pro Academic, and more than 300 commercial use cases, commercial users accessing DesignStart Pro. So DesignStart is a lot more about just providing you with IP. As I said, we have a complete hardware reference system that goes along with that, so that you can take your system, prototype it as it is, or you can modify it accordingly. We also have software that can be provided on top of that, and we are creating a very vibrant community around our DesignStart products. So if you want to ask questions about how to use the DesignStart offerings, we have a DesignStart forum, and then all the different users are sharing their knowledge and experience on these systems. And of course, ARM can provide you with additional support and training if this is required. And if you're just seeing the SoC development just as a tick box enabler for your research, we have also lots of approved design partners that you can go to and ask them to do the SoC for you. So they have been receiving all the right deliverables and training from ARM in order to provide these customized SoCs, in case that's not your area of interest. So moving on, I'm going to talk to you now about the new DesignStart product that we will be announcing today for the first time. But taking a step back, I'd like to clarify that we are taking your feedback very seriously, and we are driving our roadmap based on that. So we have launched a survey a few months ago about the use cases that you have for ARM IP. So we have contacted all the academics who have access already to DesignStart, and they gave us some feedback. So we will also be launching another survey today, I believe, and if you can let us know what you think, then we can adjust the future roadmap based on your inputs. But going back to the results of the previous survey, so we saw that many of them were well aligned with what we expected. So we saw that our research and academic community thinks that Arm IP is of high quality and they're a good fit for your research purpose, which is good to hear. But of course, there are always more things that we can do. So you are asking us to give you access to more advanced processors, the ability to do research on more cutting-edge technology, and also having pre-integrated systems that can be easy to use are also, highly, desired. Also, when it comes to delivery mechanism, you were asking us to minimize as much as possible the time from a request coming to us till the time that we are releasing something. So we have taken these two requirements very seriously when we're thinking about what kind of technology we will offer you as part of the new DesignStart product. And we also wanted to make sure that you can innovate and do research on cutting-edge topics, and one of them is machine learning. So in many cases, when people think about machine learning, they have in mind really complex learning algorithms that can only run on HPC or on servers, but this is not necessarily the case. So we are seeing the need for moving machine learning to the edge more and more for many different reasons. So better user experience, reduced latency, reduced use of the available bandwidth, better power efficiency. So there are lots and lots of good reasons why you need to be doing machine learning on the edge. And it is even important for the lowest end part of the devices, for IoT devices. And we are thinking that there is a really big wave of IoT innovation. So we're very keen to enable you with a piece of IP that will let you do your research on these cutting-edge technologies. However, the vision of the connected world cannot be implemented without having security in mind. So vulnerabilities, we can see them in the current world. So if we're going to build billions or even a trillion IoT devices, which is our company's vision for the future, then we better be really sure that this will have all the right security infrastructure. So we have to create a set of technologies under Trust Zone that go from content protection on physical memories all the way to secure connectivity between the IoT devices and the cloud. So this was another really key technology and a key enabler that we wanted you to have access to. So thinking about what kind of processor we should release to you, we thought that Cortex-M33 is a really good candidate for many reasons. So first of all, it has been released to our commercial partners approximately 1 year ago, and we are about to see the first commercial silicon coming to market, but it is not there yet. So we will be enabling you to do research on cutting-edge technology that hasn't even been fully commercialized today. It has a very small silicon footprint, so it's 80% smaller than a Cortex-A5, making it really applicable to IoT low-cost devices. And it has all the right feature set that I have mentioned before. So it has DSP capabilities, which is allowing you to run machine learning applications, especially when it comes to inference on the device itself. And it is fully enabled with Trust Zone. So all the Trust Zone technologies are part of, have been implemented within Cortex-M33. As I said, we still don't have commercial silicon available, but we have lots of partners who have taken Cortex-M33 along with the rest of our V8M processors, and they will be bringing silicon to market very shortly. And we also have a wide ecosystem of partners who will be bringing their software and tools for Cortex-M33. But as you told us, you prefer to have subsystems rather than access to a specific processor. That's why we thought it would be good to provide you with a subsystem that we call SSC200. And it actually has 2 instances of Cortex-M33. You can use one of them for secure applications and the other one for non-secure applications. Or you can do any other kind of partitioning as you see fit for your research purposes. And of course, we are providing you with all the interconnect infrastructure and peripherals, and they are all fully trust zone aware. So security is not something that has been implemented on the processor, but it has been implemented throughout the subsystem. And last but not least, when it comes to providing you with all these technologies, we have changed the delivery channel quite significantly for this one. So we have partnered up with Amazon Web Services, and we are making this subsystem available to you through Amazon F1 Cloud. So this is going to be a new DesignStart product line. We call it DesignStart FPGA on Cloud, because it is a really easy way of doing FPGA-based prototyping without having any physical board sitting on your desk. And because of the well-protected Amazon infrastructure, we can enable you with our cutting-edge technology. So you can find the AFIs and AMIs on, and use them on Amazon Cloud. These are the FPGA image, and the AMI is all the software that needs to go on Amazon host CPU in order to get started with prototyping on this platform. And this is now available. We will roll it out to some lead partners first to make sure that it is sanity tested. So if you're interested in participating in that program, please come and talk to me. And our plans in the near future is to make it available through Amazon Marketplace so everyone can have direct access to that without even asking for Arm's permission. Also, what we're planning to do is to help you add your own hardware accelerators in this system. So the current offering that we have developed is meant to be for software prototyping only, but it is in our short-term plans to add hardware accelerator addition capabilities so that you can have a full software-hardware co-development platform on the cloud. Also, we have lots of great add-on technologies that we think can be applied on top of the DesignStart FPGA on cloud and make this a complete reference system even more useful to you. So I have mentioned at the beginning about CMC Sandlin. This is an open source library for Cortex-M, all our Cortex-M CPUs, and it has pre-optimized functions that you can use as building blocks for writing your own machine learning applications. So you can have access to this library and use it either in the new M33 cloud-based platform that we are offering, or on any other M-class-based platform that you may have access to. Another piece of technology that is quite interesting is Embed OS. It is an open source free operating system that we have developed for IoT devices. And you can port it on top of the Cortex-M33 platform on Amazon Cloud. And in this way, you can develop your applications, your IoT applications. On top of that, you can also get access to Embed Cloud through our Embed OS, which is enabling you to have a better control of all the different devices in an IoT cloud, and then do advanced research based on complex IoT topologies. And last but not least, we have the Arm DS5 Development Studio platform that is a necessary tool for debugging your software and profiling your applications that go on top of our processors. And we are planning to enable the cloud-based M33 platform with DS5 as well. So a quick summary of what we have talked about today. We have Arm's Research Enablement team that can offer you lots of different technologies. We know that there will always be more things to do, so we are really keen to take your feedback, help you make the best of the current offerings that we have, and make sure that we create the right roadmap in the future so that you can do faster and easier research based on ARM technologies. Also, we have the DesignStart FPGA on cloud. We are enabling you with the SSE200 subsystem with Cortex-M33, letting you do research on IoT, machine learning use cases, and it's powered by our Trust Zone security technologies. So you can find more information at thedesignsstart.arm.com, or you can go talk to Ron and Vanessa, who are sitting at the back over there, so they can help you get access to any ARM IP you may like, or to the DesignStart products that we have just mentioned. Thank you very much. Any questions? Yes, please.
So very interesting program you presented. The access to the processors and the FPGA you presented lately. So what about the GPUs? Because I think that when you are developing at the edge, this is very important.
Yes. Yes, we are thinking about that. I haven't completely forgotten my background. I have a GPU background, and we will look into this. But we just thought that in terms of priorities, enabling people with ARM CPUs was #1 priority, especially Cortex-M, high-end Cortex-M with a new feature set that are unlocking research on so many different areas was the first right move. Then we will proceed with providing other IP. But as you know, you can have access to ARM GPUs as well if you want to use them on a specific project. They are just not yet part of DesignStart or any other platform that we are giving, we're making more widely available.
Yeah, I just want to reiterate that. DesignStart is our way to try to streamline this process, but you can make an IP request for anything to ARM. Right. Go through the process, and we'll try to help you with whatever constraints it is.
Yes, please.
Yeah, so I'm very impressed with the presentation. Thank you.
Thank you.
Question. So the basic design starts, so where we get to this M0 and M3.
Mm-hmm.
So is it more supposed to do a design exploration on FPGA, and then when you have the design start pro, so then you can start implementation in the silicon?
Correct. Yeah. So with sorry.
Yes. So for this implementation in the silicon, so one thing which is important are the RTL, but also what's important is the whole infrastructure regarding the tool scripts. So for the synthesis, for place and route. So are you also delivering the script as well?
Okay, so you have hit spot on one thing that we are doing, but I didn't fully put flesh into that. So I think that our engagement with Europractice is going to cover all of these areas. So we do have some reference implementation scripts at the moment that we are making available as part of DesignStart. But some of them are a bit old. They are only based on old technologies, old cell libraries. So we are planning to bring them up to speed and provide you a wide variety of cell libraries to use and the relevant implementation flow that goes with them. Yes, please, Brett.
So you mentioned the SSE
200?
subsystem for FPGAs on AWS.
Yes.
Is there any plan to support that for ASIC design as well?
It is not in our current plans. However, we do have silicon available of SSE200. We have a limited number of prototyping platforms, physical prototyping platforms. So please come and talk to us if you have an interesting use case for that. We are happy to enable you with that. Yes, please.
Will you get these slides or just for the picture?
Yes, yes, you can have them. Okay, thank you very much. Thanks, Jalin.
So hello everyone. My name is Jalin. I'm from Arm Education. Yes, so to begin with, why do we have an Arm Education? Oh, sorry, the slides. Okay. So yeah, as you know, Arm's success during the past. Oops. Yeah. So during the past a few decades, Arm has been very successful. So yes, there were like. Sorry about that. Somehow that's nice. Sir, can you give me a hand somehow? It automatically 10 pages.
Okay, that's fine. I can sort that. Okay, that should have done it. Oops. I see.
What's the problem?
For some reason, it's not wanting to come off that. I'll do it the long way. Okay, that should be fine now.
Okay, thank you. Sorry about that. Yes, so I'm Jialin Dou from Arm Education. Today I'm going to talk about the Arm's role in education, technology education, to help fostering engineering skills for the electronics industry. So as you can see, Arm has made huge growth. So cumulatively, Arm has produced 125 billion Arm-based processors during the past few decades. The previous success was attributed to smartphone, the huge growth of mobile and smartphones. And the next huge growth is going to be Internet of Things, as Frank has just mentioned. So one of the biggest challenges of the upcoming Internet of Things digitization transformation is the lack of talented or skill shortage for the society. So that's why we created Arm Education Department to help addressing the engineering skill gap. As you're probably aware, at the moment, there's already a skill shortage for the electronics industry. That's partially because what's been taught in the university and what's been employed in the industry has a gap, and the technology, the fast pace of technology, was part of that reason. So Arm is being in the center of this huge computer system. Arm has a responsibility to help addressing this skill gap. So that's why we have Arm Education. So within Arm Education, we have Arm University Program and Arm Education Media. What Arm University Program does is it provides freely available education kits to the academics who could help, who could use these education kits to teach undergraduate and postgraduate students about the latest technologies. And Arm Education Media address the other part of the individuals or the hobbyists who were not affiliated to the university, but they are very interested in electronics and they want to learn themselves. So looking at the university program, it was created in 2013, and nowadays we have thousands of universities worldwide adopting the Arm education kit. So it has achieved a huge success in terms of helping the industry to facilitate the skill training. What the education kit includes is it includes the teaching materials, that include the lecture slides, lab materials, and also the software, like what Plot was saying, is like DS5 or the software tools, and also some sample boards that could be used by students. And also we offer a bit of trainers for the academics. And for the education media, we have a textbook to accompany the education kit, and also the online lecture videos and the lab videos. So the students could learn at their own pace during their spare time, and also interactive quiz. So these are the roadmap for our teaching courses. So that covers 3 segments of the electronics industry. From the very top, the application design for the electronic system, including like gaming and graphics, Internet of Things, to the system level like RTOS, DSP, or Linux kernel, and to the electronics level to the like computer architecture or VLSI design, SOC design. So that's for the education kit. Our education media online course also mirrors what's available in the education kit, but shifted by a couple of years due to creating the online material. So there's a video. Sorry, I'll show you a video briefly.
6 years, but with the UK still facing a shortage in engineering jobs, a computer firm has teamed up with University College London in a bid to encourage more young people to go into computing. Tech firm Arm is offering students an opportunity to develop their computer and coding skills, as Nick Beek has been finding out.
Plotting your career path is not always straightforward, but these second-year electrical engineering students at UCL feel they're on track. They've been building their own robots and smartphone apps, which could be the next big thing.
I'm wearing a hard monitor.
And I can monitor it on the phone.
And I can see it in real time on the cloud.
It's hoped this sort of technology could help the NHS. But at the moment, on average, half of all engineering graduates are walking away from a job in engineering.
I think especially here in London, you're used to sort of the big city and you go into things like banking because they can offer the salaries and people sort of get excited by it. But I think that's definitely starting to change now.
If you want to increase your knowledge about the world or become innovative,
and they hope this can help. A new partnership between a tech company and the university. Students are given a kit to develop their own inventions.
I've never developed an Android app, so that has been really great. And it's always fun to do little projects like on the side, and I don't know, it gets you to use your knowledge. So you've got the theory that you learn in lectures, but using it really enhances that for me.
Our students have not had the chance to work on such equipment. They had the chance to work on something probably similar before, but never something as sophisticated, easy to use, and small.
What difference do you think it will make?
I think it will make them better designers. I think it will make them better engineers. And I think it will give them a chance to do more fun things.
Well, this might be pretty good fun if difficult to master, but the sensor technology they're using here and experimenting with is what's being used elsewhere to create some pretty major innovations. For example, cars that drive themselves and park themselves.
Engineering is a great subject. You can take that, you can go and be an entrepreneur, start a company, you can go and work for companies, and there's just lots of opportunities for engineering.
And this morning, at this technology and education exhibition in East London, it was announced that Google and O2 would be among those helping deliver better...
Yeah, that's an example. So to become a part of the education program, just go to Arm's website, and on resource education, you'll see education kit. If you click in that link, you'll see the, maybe not demo here. Yeah, you can, there's a form you can fill in, which you could become a member of the, our university program. So this is another example of the SOC education kit. So by using the, it's using the Cortex M0, and with the DesignStart, that's freely available, and then you could use that to teach students how to design a system on chip. Yeah, I think that's conclude the talk. Thank you.
So good morning, everyone. I'm Rhett Davis from North Carolina State University. I'm going to talk about how we have used the ARM kits in teaching as well as our research program and some of our perspectives on that and why we use it. I'm going to present, this is work I've done in collaboration with, oops, does that work? Nope, no, that's okay. This is, I've done in collaboration with my colleagues Eric Rotenberg and Paul Franzen at NC State, so I want to make sure they get credit for this stuff as well. And then I've listed all of the graduate students who have been involved in this. So if you don't know me, I like making chips, but I'm not just interested in making any chips. I'm really interested in making chips that work, which kind of makes me unusual for an academic. I find that once you get above about 100,000 gates, the chips that work in an academic setting anyway are the exception rather than the rule. And you know, that's kind of okay. If you're doing architecture research, you can still learn an awful lot from making a chip that doesn't work. So I don't want to poo-poo that too much. But if you're like me, and what you're interested in is the design process and the design methodology and the design flows, then having a chip that doesn't work is kind of useless to you, because how do you know whether actually if the flow doesn't, if the chip doesn't work, then the flow that was used to make it is uninteresting. So that kind of gives you a framework to understand where I'm coming from in using the ARM tools and the ARM IP rather. So let's think in terms of the kind of system that I'm very interested in building, which has been mentioned a fair bit here yesterday, which is 3D stacking of systems. I've got a picture of an AMD high bandwidth memory, which I'm just kind of including because I love the picture, which is sort of indicative of the sorts of things that we're trying to prototype, as well as a conceptual stack from a project that we were doing at NC State that I'll talk about here in a minute. You've got benefits of heterogeneous integration, so having DRAM integrated with the logic. You can also get benefits from miniaturization, shorter wires. These are the different kinds of things that we're interested in research projects showing an advantage from. So the real big question that has been burning me up is, how do we make this easier to prototype? How do we make this easier in a university setting to prototype things that work, to show our value? And I've included my conclusion slide here because I know that I'm standing between you and a coffee break. So to make it short and sweet, what's the main message that I'm trying to get across? And so the first is that, well, what makes it hard is essentially complexity. And that means that you've got lots of cells, which means, and also lots of behavior, which makes it very difficult to know how much power they're going to dissipate, how fast they're going to run. That means that in the design process, and I'm thinking mostly of the physical design process of taping it out, as well as the coding up of the RTL source files that make it all work. You've got very long run times for simulation as well as place and route. You've got huge files. And so that makes this process very complicated. So now if you think of the little neural net, another popular topic in the last couple of days, that each designer has to run in their mind, that essentially runs down to few samples. So you're trying to get this very complex process to work with very few trials. And we could even think of actually building, machine learning tools to help this process. But if you have very few samples, that's very few opportunities to get it right. And that's essentially the problem with getting all this to work. So that leads to uncertainty, well, depending on how you look at it, uncertainty or inaccuracies. You don't really know whether the circuit is going to be working as you expect. So why does ARM IP help us with this? And the main thing is that it just works, that in these state-of-the-art debugging flows and design flows. So that means that we spend little or no time actually trying to solve problems with our design, and we can spend all of our time debugging the flow to figure out how to mitigate these problems that I mentioned. Because so often when we do these large designs, we can spend days or weeks trying to track down a particular problem, only to find that it was a problem with the design that we have created rather than the flow, that the flow is actually working properly. So it helps us to separate those concerns. And it does that with a consistent organization and management of the complexity of the whole system, and helps us to separate these good design flow tweaks from the bad ones. So that, in a nutshell, is why we use it. So let's see, how are we doing? Given that we only have like about 8 minutes to talk about the rest, and I have about 15 more slides, let me just give you a quick flavor for this, and really try hard not to go into the details, but to give you some slides so that if you want to ask me about the details, you can. So first, one slide about how we use it in teaching, because that sort of drives everything else, and then just a little bit about 3 different research projects where this comes in. So here is, in one slide, is sort of a picture of the system that we use in a course called Electronic System Level and Physical Design, where we go all the way from an ESL transaction level modeling view of a system down to the physical design and verification at the signal integrity and power integrity level. And it's all done in one semester. We use this ARM-based SoC to do it, which is built around a Cortex M0 DesignStart processor, as well as Synopsys bus and memory controller models. And then the goal is for them to build an accelerator that sits on the system and then to show the whole system working, again, from the highest level of abstraction to the lowest. It's got about 20,000 gates total, which is enough to sort of force them into this very structured methodology where they don't have time to really hack things, but they have to observe this very careful methodology and show the whole thing working. It allows them to sort of see how their estimates of power, performance, and area change from that highest level of abstraction all the way down to the bottom, so that they're used to seeing that certainty grow rather than sort of becoming less certain, and so that you can converge on a finished system. So we also use ARM fast models, which is that transaction level modeling environment. And I'm hoping that that will soon become part of the educational offering. And one day, hopefully, we will also incorporate this into the synthesis scripts so that you can actually place and route designs. Things have to change before that works. We have to get agreements to use these kinds of tools and these standard cell libraries in an education environment, but that's all things that we're working towards. So that, in a nutshell, is what we use. Just a couple things about 3 projects. One, and probably the one that was my favorite, which I'm going to have to try the hardest not to talk forever about, is one where we actually built this 3D stacked microprocessor. We had a stack using face-to-face bonds with a high-performance big core on the top, a low-performance small core on the bottom. There are some details about it. It used about 1.5 million gates. It was the biggest design that I've ever worked on. Actually, I've joked with the research guys when I was talking about this before. It's kind of more of a big core and a slightly less big core. So we can talk about that more offline. And it used a MIPS ISA. So this was a design that was driven by Eric Rotenberg in our department. Now, of course, why am I talking about how ARM helped us if these used a MIPS ISA? And well, that wasn't part of my part of the project. That was Eric Rotenberg's part. But the main reason why I bring up ARM here is that we had to use the ARM SoC to debug the flow. That we had to build an entire physical design flow using mostly industry tools with a few point tools to stitch them together into this 3D stacking environment, as I described there. And of course, we started out with about 100 gates to show that it was working, and then they throw in the 1.5 million gate system, and it just doesn't work. So what do we do to fix it? Well, the first thing that they did was, having taken this ESL and physical design course, they throw in the Cortex-based SoC, and they debug the whole flow, getting it to work there. And I really don't know if the chip would have ever worked if we had not done that, because we debugged so many problems with the flow by using the Cortex SoC to drive it that it was really a lifesaver for us. And the experience of having had the class really sort of raised the expectation in them to do it that way, and that's, I think, why it worked out. It also allowed us to do some other interesting tests, which I won't go into here, looking at the benefits of the relative benefits of via pitch, as well as looking at different floor planning strategies, reminiscent of the thing that the gentleman from Synopsys talked about yesterday in terms of technology and architecture co-optimization. It made all of those sorts of things possible for us. I'll also talk a little bit about our measurement results. Again, the main purpose of mentioning all this is that because of the ARM IP, which helped us to debug the whole flow, it raised this expectation, and it enabled all of these measurement results, which I don't know that would have been possible had we not had that experience. And we showed that we could migrate a thread within 100 cycles from one core to the next. We also showed that a crisp quantification of the ultimate benefit, which was that by having this heterogeneous stack, we were able to get slightly less energy than using just a single large core, or slightly less energy than, sorry, what am I saying here? Less energy. This is where I get tripped up because I'm not the computer architect. Right, so the two-wide was we want to show that for this range of benchmarks that we can use less energy than by just having the large core, but by migrating certain parts of the program to the smaller core, we can actually get a smaller amount of energy. Also, if we just had the small core, the one wide, that we could get a faster execution by migrating parts of it to the two wide core. And so we were able to show that by having the stack, we could sort of get something that was better than having either one. And that was the main research goal. So it was successful, and again, was thanks to having that ARM IP that it was successful. So now moving this on into saying, well, what if we really did want to have a a machine learning algorithm to do this kind of physical design for us? Now that we have this very structured approach, we can start to talk about putting a machine learning loop around this to sort of figure out, well, how can we, instead of training our own neural nets or having the physical designers train their personal neural nets to figure out how to put together this physical design flow, can we turn our physical designers into trainers and say, now don't just do the button pushing yourself, but become the trainer that trains the machine learning algorithm to push those buttons for you and explore to find the best path through the physical design flow. So that's another project that we have going on now. It's funded by this machine learning research center that we have with Georgia Tech and Illinois. Again, I don't want to talk too much about that. I will show you one picture here, which was the picture that we get more traction with than probably any other, which was a simple experiment that was done by one of our PhD students, Wei-Yi Chi, who showed that by putting a very simple machine learning algorithm outside this flow, that he was able to build a surrogate model for how the system should work that allowed him to do basically in 4 iterations what it otherwise took him 17 iterations to do. I think that's what he said. 20 iterations, no. So he did within 4 iterations what it took another designer 20 iterations to do. Because rather than just randomly trying spots and knobs, the surrogate model figured out what the best settings were, or rather, a predictable amount of settings, and then allowed him, it didn't completely remove the designer from the loop, but made him more efficient. And of course, what did he use to drive this? Well, you guessed it, it was that same Cortex SoC that we used from the class. And so if we hadn't had that, and if it hadn't been debugged and working, there's no telling whether or not he would have ever had success with this. And now we are doing more studies with this. We are doing research in machine learning to try to figure out, well, how many samples do we need of these different designs to try to figure out what the range of possible designs are? How do we optimize that? What machine learning algorithms, what models are the best ones to handle the sort of the random behavior of the tools and the difficulty of understanding this complex behavior? And as you might guess, the Cortex SoC, as is shown on the right here, is always the one that is sort of our pipe cleaner, if you will, to make sure that everything is working. We quite often find that many of the samples that go through this are just bad, of course, because it's very complex and because it's very error-prone. And the way that we always know which ones are bad or not is that we compare it to the Cortex and we say, is it working as well as that one? And if not, then we know that there's something we have to go and figure out. So that is, we're just about out of time, but let me just mention one last thing, which is universal power models, which is something that's also very close to my heart, which is just looking more towards the future, looking at bigger picture issues of computer architecture. I think that one of we all say that we want system-level power models, and one of the reasons that those are so pressing to be able to analyze power at the system level is because of the need for reliability. These parts wear out. And there's interesting research that I've referenced here from 2014 of people looking at how do you optimize the way that you schedule and distribute workloads and power so that you can actually make sure that these systems don't wear out. In fact, you see that there's different failure mechanisms that are exposed based on how different parts of your chip heat up. And I would encourage you to read that paper if you're interested in more about it. But where I'm coming at this from is the problem that all of the research that's out there in temperature reliability co-optimization is based on unreliable power models. And the problem with that is that if your power model is unreliable, then I think your co-optimization is also going to be unreliable. And the reasons for that, I've just got sort of two images here that illustrate why they're unreliable. The first is, on the middle there, is showing how the leakage power estimates are unreliable. First, that if you just were to look at how a NAND gate leaks relative to an inverter over a full range of process voltage and temperature variations, then you find that there are some cases where they differ by a factor of 60. And so if your leakage powers can differ by a factor of 60, or maybe they're about the same, then how do you know how much leakage power you really got? Then dynamic power on the right. The behavior of these systems is so complex, it's very difficult to know how much dynamic power they're consuming at any point in time. So, and all of the reliability mechanisms are essentially based on this Arrhenius equation, which shows how temperature basically has this exponential variation with, the reliability mechanisms vary exponentially with that temperature, and temperature, of course, depends on power, so you have to have more accuracy there. So this is why I've been very heavily involved with different IEEE standards organizations, in particular the IEEE P2416 group, which ARM is involved with. And we need to create examples to help move the standard forward. And the ARM SoC has always been the example that we use to create examples to help inform the committee. I've got some of the plots that we have shared with the committee to drive this forward. And one of the interesting questions that always comes up is, well, would it be easier to just have me keep creating the examples, or would it be better to diversify the effort among the standards committee and use an open source processor like the RISC-V or this MIPS example that we have up at the top that I mentioned initially, and that way we could have an open platform for which everyone could share and look at the results. But what we keep finding step after step after step is that it's the effort that's required to use those open platforms is so huge that we just make so much more progress by just using the ARM IP and just having me all do it myself, that I don't know that we would have ever gone as far as we've gotten if we hadn't used the ARM IP. So that is where I will stop it, and we can go get some coffee. Thanks for your attention. Although I will leave you with one fun thing here and one reminder, which is to always be skeptical of your intellectual property, and I'll ask for a quick show of hands here. So which one of these is the real die photo? Is it the one on the right, or is it the one on the left? So how many think it's the one on the right? All right, how many think it's the one on the left? A couple, okay. Well, it is in fact the one on the right. This one on the left is a total fake that we put together because the one on the right is just so boring. When you show your chips, no one wants to look at something like that and say, yes, we spent 3 years and $1 million creating this thing that just looks like nothing. So, so one of our engineers doctored this one on the left here. But again, this drives home the point, which is that it's very easy to make something that looks like it works, but much different to actually create something that works. So thanks for your attention.
Okay, time-wise, I think we're doing well. We can have a 15-minute break and come back for the rest of the presentations by the professors.
Just one question.
Yes, sorry.
So in this machine learning exercise to get the circuit model out, were there parts of the
You said, were there faster models?
No, parts of the model. I mean, the flow, rather. Parts of the flow for the surrogate model. Were there parts of the design flow that were lending themselves better to the machine learning exercise?
Yeah, I think that's going to be a really complex answer. I think we'll have to take that one offline. But I think the short answer is, well, we're not really sure. They're all very noisy. And so most of what we've done at the current point is show just how much uncertainty there is. We're looking at the whole flow end to end, kind of like a system designer would look at it. And there are other researchers that are sort of breaking it down into individual pieces. But then kind of therein lies the problems. It's the interactions between all the different pieces that really matter. All right, thanks.